statistical mechanics in disordered systems. So, how do you say that?
Okay, thank you. Good morning. Okay, first of all, I want to thank the organizers for inviting me to be here to speak for you. Well, in fact, I am Argentinian, but I live in Brazil since many years ago. I work at Fluminense Federal University in the city of Rio de Janeiro, that is in the city of Niterói, excuse me, near Rio de Janeiro. Well, I am a statistical physicist, so I am a bit out of topic here in this school because I'm not a condensed matter physicist nor a quantum physicist. But I will speak about some topics that have a lot of phenomenology in common between classical and quantum physics. I am more of a classical physicist. Well, I have several interests in research in physics from statistical physics point of view. One of them that I have been working since many years ago is the non-equilibrium dynamics of disordered systems. That is the topic I will talk to you in these three lectures. Well, the plan of my lectures is basically the following. Today, I will introduce the problem of slow dynamics in non-equilibrium disordered systems. We will define what is slow dynamics, what do we understand for slow dynamics as opposed to fast dynamics, originated in the disorder or frustration in many body systems. Slow dynamics is characterized by two particularly interesting for me ingredients that are called aging and memory. We will define what do we mean by aging and memory in slow dynamics and these kind of systems. And after that, we will focus on a particular model that is called the SSK model, the spherical Sherrington-Kirkpatrick model. It is a very simple model, you will see, and we will be able to go through the calculations to compute the slow dynamics of this model. So this is kind of an exercise. I will use this model as an example for the different topics I will speak about in the 3 days, and I will be back to this SSK model to illustrate not only slow dynamics, but also the topic in the second day that will be non-reciprocal interactions. Non-reciprocal interactions is another area that has many in common between classical systems and quantum systems. In quantum contexts, it's say non-Hermitian quantum mechanics. And there are many examples in which the interactions do not obey basically Newton's third law. So when interactions are not reciprocal, new physics, different physics emerges. I will, as I said, focus on classical systems with non-reciprocal interactions, and will try to tell you something about the physics of the SSK model with non-reciprocal interactions. In particular, the Langevin dynamics. We will define the Langevin dynamics, that is a prototypical out-of-equilibrium dynamics for many body systems. Of course, it originated on classical systems, but it emerges also in effective theories of quantum systems. So I think it will be useful for you if you work with quantum systems, that I think it is common here in this school. And in the third day, I will speak a bit about integrability, integrable systems, and the measure that describes the statistics of integrable systems in the thermodynamic limit, that is called the generalized Gibbs ensemble, the GGE. And again, we will illustrate this situation, the physics of an integrable system with the same model, with the spherical Sherrington-Kirkpatrick model. So in this sense, I like this model very much because it allows to study in a certain detail very different situations. Say it is a disorder model, we will define it in the following, a model with a disordered interaction, so it has all the phenomenology of a disordered many-body system. But we will see in the third lecture, for example, that it can be mapped to an integrable model when we add a kinetic term and we define it from a Hamiltonian. So we will describe the Hamiltonian dynamics first. It has some interesting features that derive from the integrability of the model. It has n constants of the motion, n is the number of degrees of freedom. And it turns out that the SSK model can be mapped exactly to this model, which is integrable. And so at the end, we want to explore a Langevin dynamics that allows us to sample in equilibrium the generalized Gibbs ensemble. That is the measure that describes integrable models. So this is the outline of these 3 lectures. Hopefully, if my timing is more or less correct, we will be able to go through the calculations. My aim here, as this is a school, is not to give only a seminar and tell you about the things that I am working on, but to open a calculation. And this, so you can learn how we can illustrate the concepts that we are speaking about. And this SSK model is particularly useful for that because you will see that it's a very simple model, yet it is non-trivial. So it shows all these kind of different things that have many applications in different areas. So okay, let's begin with the Ising model. I think in general it's a good starting point for a statistical physics course. The Ising model that is doing 100 years today, this year. Okay, the Ising model undergoes a phase transition, as you probably know, at a critical temperature from a high temperature disorder phase. I will speak about the classical Ising model, so the original, the model that Ernst Ising published about when quantum mechanics was beginning to be developed, but the model that Ising defined and published about was a classical model, in spite that the spins are discrete variables. So the classical Ising model, the spins are binary variables, plus minus 1. In 2 dimensions or above, it goes through a phase transition at a critical point, at a critical temperature. So high temperature paramagnetic or disordered phase, and below the critical temperature, the system enters a ferromagnetic phase with a preferred orientation of the spins. So magnetization, which is the order parameter of the model, turns different to 0 below the critical temperature. This model has many interesting properties, in spite of its simplicity. The free energy has only one minimum, of course, at high temperatures, which is characterized by an order parameter that is 0. It is a symmetric phase. At the critical point, the model suffers a symmetry breaking, phase transition, so 2 equivalent solutions appear exactly at the critical point. And there is a symmetry breaking. So either because we apply a small magnetic field or by a fluctuation, the system in practice, in the laboratory, will be observed at one of these two equivalent directions. This is the breaking of the up-down symmetry of the model. Now let's speak a bit about dynamics, that is our topic. If we measure, for example, magnetization, that is the basic quantity that characterizes the order in this system, and we are at a temperature above the critical point in the disordered temperature, we can initialize the system at some temperature, and if we quench but staying above the critical temperature, the relaxation to equilibrium will be fast. And this will be what we call fast dynamics, will be exponentially fast. So the system will relax exponentially to equilibrium with zero magnetization, of course, zero order parameter. The same will happen if we are below the critical temperature and initialize the system with a small magnetization, so with a broken symmetry state, whichever small it is, and we let the system relax. It will relax to equilibrium at the temperature of the bath, say, of the thermal bath, and it will relax exponentially fast to equilibrium. So when a system is in equilibrium, in general, independent of the initial state that we choose, it will relax exponentially fast to equilibrium. It will equilibrate. This is a fast dynamics. This is, in some sense, not very interesting dynamics. So that is what we understand by fast dynamics. Okay, very different relaxation happens, for example, when interactions show what is called frustration. In the picture on the left, there is a square lattice with an antiferromagnetic easing model. So the spins minimize the energy by being anti-aligned. In that lattice, in the square lattice, the antiferromagnetic easing model has no frustration. Say it has a ground state, also two equivalent and symmetrical ground states, in which each spin is surrounded by 4 other spins that are anti-aligned to it. So again, the system may relax to this state exponentially fast if we initialize the system at low temperatures, but in the broken symmetry phase. But for example, if we have a different kind of lattice, the triangular lattice, probably you know, because this is the classical example of frustration. In the triangular lattice, the antiferromagnetic model shows a strong frustration, because you can see that if we try to align or to anti-align, in this case, the spins, we can begin with these 2 spins that are anti-aligned. And for the third, we don't know what would be the optimum configuration, because in each configuration of the spin, up or down, it will be aligned with one of the neighbors. So this is what's called frustration. Say the system, there is no unique ground state. Of course, in a large lattice, frustration will be the origin of a lot of degeneracy of the energy levels, because many spins will be in a state that we can flip them and go to another nearby state in energy, or practically don't change the energy in the large n limit, say when the system is near the thermodynamic state. If we have a strong frustration, like in the antiferromagnetic easing model in the triangular lattice, we can guess that relaxation dynamics will be problematic in the sense that the system will have some trouble to find low-lying, say low-energy states as it tries to relax. This probably the prototypical example of this kind of relaxation when frustration is present is seen in glasses, in window glasses, in real glasses. Glasses, you know, microscopically are amorphous systems, so there is no lattice, there is no symmetry in the lattice at which the system relaxes in the ground state. And this is because of different reasons, mainly because the molecules that form glasses have different sizes and different geometries, and they struggle to find low energy states when the system is cooled, for example, in a quench, is quickly cooled. That is the way glasses are produced from a liquid state at high temperature to the solid state at low temperatures. So glasses present this picture of a glassy landscape. There are many, say, metastable states in which if we quench the system, if we produce a rapid cooling of the system, it will lose kinetic energy, and it will be, say, in a region of phase space, of configuration space, in which it will be trapped. It will be very difficult for it to go out of this region, of this local minima, and try to relax more. The pointer is not working very good, sorry. Okay, here I think it's better. Okay, so in this kind of picture of situation, the dynamics, the relaxation dynamics typically will not be exponential or exponentially fast. In general, it would be described by power law decays, by algebraic decays, because the system will relax much more slowly to equilibrium. For example, because it finds energy barriers that will be difficult to surmount in order to search for better states in energy, say for low-lying states in energy. So the system will go through this local minima, trying to relax. This is really very strong, say, in terms of the relaxation of the system, and it is it produces, for example, the fact that the system may stay out of equilibrium for any laboratory time scale. So it is difficult to assess if a glassy system is in equilibrium in laboratory time, because the time scales to relax may be infinite, maybe very, very large. Okay. If you have some question, please interrupt me and we can talk as I present this. I don't know if this the concepts are simple, but I don't know if you are familiarized with them, so I may stay a bit more than necessary in some points. But well, anyway, you can stop me and ask me. So this is another picture of what is called a rough energy landscape. So a landscape, or say the state space of the system, has many local minima. And if we are studying relaxation, we can think qualitatively here. Qualitatively that the system will visit say, a rough phase space, and it will have some difficult to go from low-lying states to other low-lying states. Well, if we measure magnetization or another parameter, probably in this kind of systems, we will see a power law relaxation. It is a signal that there is slow dynamics. But in order to characterize much better slow dynamics in a system, we have to look at least to 2 times quantities. And we will see that, for example, defining 2 times correlations and responses, we can have a much more rich picture of slow relaxation. And this is what is usually done. In particular, defining 2 time quantities, this is the autocorrelation function. You see that there we sum over the spins, so it is autocorrelation, but computed at 2 times. So we measure how the system departs from itself. We fix a small time at one point and measure correlations from this time. We will define the smaller time as the waiting time. Say the protocol that we are thinking is a quench. At time t equals 0, we prepare the system. For example, we prepare the system in a high temperature initial condition, say in a fluid state, in a liquid state, and we quench it instantaneously to a low temperature, or in a quantum system to a point in interactions with a lower energy. And then we wait for some time up to t prime or t waiting time. So we let the system relax from the initial quench up to a predefined waiting time. And at the waiting time, we begin to measure correlations or order parameter of the observable that we want to study up to another time, larger time, t. The fact is that if the relaxation is fast, the system quickly goes to equilibrium, and you know that in equilibrium, the dynamics is stationary. So time-dependent quantities depend only on the difference of the times. So there is a time translation invariance. So if we let the system relax up to the waiting, and the system was already or relaxes fast to equilibrium, then all measurements from this time will depend only on the difference between t and t waiting, that we will call tau. Because the system quickly enters a stationary dynamics. But in glassy systems, in disordered systems, this usually does not happen. So the time that we wait until we begin to measure matters, and we will measure different quantities, different values of the observable that we are measuring, depending not only on the difference between the times that is typical of an equilibrium dynamics, but on the 2 times that we are looking at, or on t waiting and tau. This is what is illustrated in that figure. Each curve corresponds to a different waiting time. These are results from simulations on a frustrated lattice gas. Each curve corresponds to a different waiting time. So you see that the curves, say the relaxation, the autocorrelation, not only depends on the difference of the waiting time and the largest of the times, but depends on both times. For a different waiting time, we see a different kind of relaxation. The system follows a different curve. Well, this is a signal of out of equilibrium dynamics. This is a clear signal of out of equilibrium dynamics. If the system would be in equilibrium, all these curves will collapse onto each other because the relaxation would depend only on the difference of the two times on tau. Here in the horizontal axis, you have to read tau, not t. So the horizontal axis measures the difference between the measuring time and the waiting time, tau. So say at tau equals 0, the autocorrelation is 1, and we measure how the system departs from itself as time goes by. We can see that for small waiting times, the relaxation is faster, is more or less fast. It decorrelates from itself more or less quickly. But as the waiting time is larger, the curves began to develop a plateau. And you can see that there is a region in which they collapse onto each other. Excuse me, it's difficult for me to follow the pointer because it does not point to the actual region I want to illustrate. Okay. You can see that for large waiting times, the curves tend to collapse on each other, and they relax to a plateau. If you think on the picture of the rough energy landscape, this is telling us that basically the system from the waiting time, that it is large, so we wait a large time, whatever it means, but we wait in the laboratory a large time before we begin to measure our observable, and immediately the system enters a limited region in phase space or in state space. So the correlation is large. You see that this plateau develops at a rather large value of the correlation. So the system struggles to decorrelate from itself or to relax. This is because it gets trapped in a limited region of phase space. That will probably correspond to some local minima from which the system will have to go through some energy barrier, for example, in order to relax. But in any case, if we wait long enough, at some point, the system will relax and go out of equilibrium. The plateau, in which all the curves for different waitings collapse, is called quasi-equilibrium regime, because it is not an equilibrium regime. At the end, the system will go out of this plateau. So when we see that it went out, we realize that it was not in equilibrium. But it depends on the time scale we are looking in the laboratory. So it is a tricky point. Say, what are the time scales that we measure these glassy dynamics?
Question.
Yes.
So in these plateaus that are telling us that the system is getting trapped in some local minimum, that doesn't necessarily imply that for each run it's the same minimum. It could be like a different local minimum of the potential landscape, right?
Yes, yeah. It depends on the realization. It depends if you are simulating on the particular run of the simulation. So these are averages over many simulations, and also are averaged over the couplings that are also random variables. So this is a typical of this is an average behavior.
it's still interesting that even though it could be different minima, each different minima sort of behaves roughly the same way because the plateaus are similar, even though it could be.
Yes, okay, good point. Again, this is the average behavior. When you look in detail at particular runs, or if you are an experimentalist to a particular experiment, you will see a great variation in the outcomes. So there are many situations in which the system will get trapped in a particular and probably not very probable situation. This may cause, say, important consequences to the fluctuations. So at this point, we are not looking at the fluctuations. But of course, when you look at each realization or at each simulation, fluctuations will be typically very large. This is the average behavior. Okay, this behavior, this fact that the system initially seems to equilibrate, but eventually goes out of equilibrium, is what is called aging. So in that simulation, this sector of the relaxation is not well developed. But in general, we will see this kind of situation. So this is waiting time 1. This is waiting time 2. Excuse me. This is T waiting 2. This is T waiting 3. With T waiting 1 less than T waiting 2 less than T waiting 3. So as T waiting grows, as we said, the system, the relaxation proceeds through a plateau in which there is time translation invariance, so kind of equilibrium dynamics. The system is in a sector of large correlation, so the system has not been able to decorrelate from itself. But after some time scale that depends on T waiting, we will see this more in detail when we look at the model, at the SSK model, in which we will be able to compute the things. But this is the phenomenology. This is the basic phenomenology to have an intuition of what is going on. After some time scale that depends on T waiting, the system, we said, it goes out of equilibrium. It decorrelates, and it finally decorrelates in logarithmic time scales. This phenomenology is what is called aging. In the aging regime, there is scale invariance in the times. So this is an analytical property that is very, very, very special, say very characteristic of the aging regime. So the two time quantities depend on both times, not only on the time difference. The system is out of equilibrium. The relaxation is slow, and there is time scaling between the two times, the smaller and the larger time. The behavior in the plateau is called weak long-term memory, because we can interpret that as some kind of memory that the system has developed during the relaxation up to T waiting. Remember that we, at the initial time, we make a quench, a sudden quench, and we let the system relax up to T waiting. So after T waiting is what we are looking at here. We see that there is some memory of the initial state up to some point in time. So it is a weak memory. It is not, say, a long-term memory, but it is weak. in spite that we will see in the model that these time scales are very large. In fact, they go to infinity. So when we saw this, say in the laboratory or in a simulation or in an analytical example with an exactly solvable model, we can conclude that the system never reaches equilibrium. These kind of systems remain out of equilibrium for infinite time scales, because if the waiting time grows, this continues to happen. The system relaxes slowly, but after some time scale that can diverge, it goes out of equilibrium. So these systems never reach equilibrium. Glasses are this kind of systems. These are called the prototypical out of equilibrium system. Glasses always have some more deeper minima to explore. So in laboratory time scales, glasses are out of equilibrium systems. In spite of window glasses being solid state, say. So we think, well, they are in equilibrium. If we measure, for all practical terms, the system is in equilibrium. But formally, if we look at the microscopic dynamics, the system is not in equilibrium. It's not perfectly in equilibrium. Because, for example, it will show aging.
Are you using the idea of equilibration in a different sense of thermalization in this case? I mean there is some kind of confusion.
Well, for me, say from a classical point of view, it's more or less the same.
Okay.
Say what I mean for equilibration, and say it is a weak definition of equilibration for me. For me, equilibration is time translation invariance. It's stationary dynamics. But it is not synonymous of equilibration. But in this context, it is only what we need to know. So in order to separate what is stationary dynamics from what is a non-stationary dynamics. So equilibrium, more or less. And well, and when I speak about equilibrium, I am thinking of a thermal process. So putting the system in contact with a thermal bath. So in that sense, it is thermalization. But for me, it's more or less a synonym of equilibrium.
That simulation was done with a bath. I mean, you're using the classical Ising model connected to a bath. Okay.
Yes. All this is classical, yeah.
Okay.
All this is classical.
Yeah, thank you.
But in spite of being classical, as I said, the phenomenology is also seen in quantum non-equilibrium many-body systems. For example, in condensed matter systems in which, for example, a metallic matrix is filled with some impurities or doped, for example, in doped antiferromagnets that are important for the phenomenon of high temperature superconductivity, for example. This phenomenology is seen at very low temperature. There are spin glass phases, and they are not very good understood. And this slow dynamics is present in those systems also. So it is not only, say, a characteristic of a glass, of a window glass. I speak of glasses because I am used to. But this phenomenology is present in quantum systems also.
And there is also disorder in that simulation, right? Because
yes,
the Hamiltonian
in this simulation,
showed,
there is disordered interactions, yeah.
Yeah.
Interactions are disordered, yeah.
Okay.
Are random variables. So, for example, in a doped system, you may think that, for example, if the doping atom is magnetic, these magnetic interactions, the atoms are positioned at random points in the matrix of the model, and they will produce this slow dynamics at low temperatures. Okay, let me see. Up to what hour? Okay. Okay. So this is the basic phenomenology, what we have been talking about. Now let's introduce a particular model that is the spherical Sherrington-Kirkpatrick model, the SSK model. This model is a spin glass model. Spin glasses are defined by disordered interactions. Interactions are typically random variables. So in this model, we generalize the Ising model. The Hamiltonian is a two-spin Hamiltonian, similar to the Ising model, but different to the Ising model. The variables are not binary. They can take any real value, but subject to a spherical constraint. This is the spherical, it is why it is called the spherical Sherrington-Kirkpatrick model. So we have a Hamiltonian with real variables, the spins are real, and there is a global constraint between them. So any state or configuration of the system lies on the surface of a sphere in n dimensions, say an n-1 sphere. This spherical constraint is responsible for, say, the non-trivial behavior of the model. If not otherwise, the model would be trivial because the variables are real and would not be bounded. So this spherical constraint somehow bounds the configuration space and gives an interesting and non-trivial behavior. But of course, this is kind of toy model. This is not a model representing any particular or real material. The interactions are disordered in general. They are chosen, say, when we are modeling it from the Gaussian orthogonal ensemble. So the elements, the interactions are random Gaussian variables. They are symmetric. I said this because tomorrow we will speak about the non-reciprocal model, but here the interactions are symmetric. They have this average value and square average that you see are scaled within. This scaling within is because this is a completely connected model, so each spin is connected with every other spins, and if we do not scale the interactions with this n factor, the energy, for example, would not be extensive. So this scaling is to make the system extensive because of the completely connected situation. So because it is completely connected, it is somehow also a mean field model. But it is a non-trivial mean field model, as we will see. In the thermodynamic limits, this matrix that defines the interactions, that disorder the interactions. So say if we do a simulation, we will have different realizations of the matrix of interactions. We have to repeat many times the simulation and average over the disorder. In the thermodynamic limit, this matrix from the Gaussian orthogonal ensemble has a distribution of eigenvalues, an average distribution of eigenvalues that is given by the Wigner semicircle law, that it is this law. So if the system has n degrees of freedom, we will have n eigenvalues. We will see that the eigenvalues and especially the edge of the spectrum will be very important in order to, it will somehow govern the long time dynamics of the system. Semicircle law. It goes from -2 to 2. It has a sharp edge that is important in order that the system has, say, normal properties. Wigner law. And because we know the distribution of eigenvalues of a matrix with Gaussian, real Gaussian elements, we will be able to use results from random matrix theory. That is also an important thing in order to solve the model exactly. We will see that the dynamics, the out-of-equilibrium dynamics, can be solved exactly using tools from random matrix theory, say basically results that come from the Wigner law in the thermodynamic limit. When we have a correction, say finite size corrections, of course the distribution is rounded here, and it is represented by another phenomenology that is described by the Tracy-Widom distribution. So the dynamics is a bit different when the system is finite than when we study it in the thermodynamic limit. Well, the SSK model has this phase diagram, 3 phase transitions depending on the value of J. J here represents the average ferromagnetic interaction. So if we have a ferromagnetic component, there is a transition. Okay, doesn't want to point. It has a ferromagnetic spin glass ferromagnetic transition at J equal 1. Ferromagnetic, okay, it is represented by the usual order parameter. The spin glass transition, it is represented by a more complex order parameter. I won't enter in details of this order parameter. We will define it within this model dynamically. We will see that the plateau in which the system enters this quasi-equilibrium regime relaxes to the order parameter of the spin glass phase. So we can think of the order parameter as this value of the correlation at long times when the system is in a low temperature situation. The equilibrium, the thermodynamic order parameter of spin glasses is a more complex quantity, but it is related dynamically to the value of this plateau in the autocorrelation function. We will be more interested in the thermal transition. Say at T equal 1, the system undergoes a phase transition from a spin glass phase to the paramagnetic phase. In fact, we will be working with J equals 0, so without a ferromagnetic component, only symmetric Gaussian interactions. So we will have only spin glass paramagnetic transition, and we will define the Langevin dynamics in order to study the relaxation dynamics to equilibrium of the system, and study the Langevin dynamics at T equals 0. The Langevin dynamics can be exactly solved at any temperature, but here, as we have only one lecture, we will focus on the T equals 0. That is, of course, simpler to describe. So, in order to study relaxation and dynamics in this model, we define the Langevin dynamics. I'm a bit frustrated because I can't point, I can't use the pointer. No, the pointer is not working fine. Okay. We define an overdamped Langevin system of equations in order to study the relaxation dynamics. Again, we are thinking of a quench, of a sudden quench from a high temperature to a low temperature. That it will be the situation, say, in the laboratory. In this case, the inertial term, say the second derivative, is much smaller than the dissipative term. So we can model these dynamics with the overdamped Langevin dynamics that is given by this set of equations. So we have n coupled equations, the gradient of the Hamiltonian, say the variation, and the noise term that defines the Langevin equation, a noise term, a noise, a random force that we define with these statistics, zero mean and delta correlated. So it is delta correlated in time and in between the dynamical variables, and T is the working temperature of the quench. This comes from fluctuation dissipation, say this relation between the correlations and this value. So with this definition, in general, the Langevin equation guarantees that the system will sample the Boltzmann measure at long times. The system will equilibrate at long times in this sense, that the dynamics will sample the Boltzmann equilibrium measure. Okay, here you can see that we have incorporated, say, the spherical constraint with the Lagrange multiplier. Z of t is a Lagrange multiplier that has to enforce the spherical constraint at each time. So it is a function of the time. It's not simply a constant or a function of the variables, but it is a function of the time. This quantity will be very important for this model, and we will see that it encodes all the complex behavior of the dynamics of the model. So we will try to solve the system of Langevin equations. Will we solve them exactly? And in the process, we will have to determine the Lagrange multiplier self-consistently. And with this, we will be able to obtain the exact solution of the dynamics, and then look at what we want to look, that is the long time asymptotic relaxation. Okay, so we performed the variation of this Hamiltonian. Well, finally, this is an external field term that it is introduced if we want, for example, to compute responses. Say in this lecture, we will not compute responses, but they are, the difficulty in order to compute them is the same as to compute the correlations. So it's very, very similar. Okay, so we perform the variation, and we end with this equation, with this system of equations, or Langevin equations, which we will try to solve. So from now on, we will enter the computation of the autocorrelation. In particular, we will be focusing on the autocorrelation function and on the magnetization, say, on the average value of the local spin. The computation is really simple, I think. So I hope we will be able to follow it. And again, as this is a school, I think it is useful to see an actual computation in a model. Well, you can see that this dynamical equation is linear. So this is why we will be able to solve it, because the equation is linear. So, well, when we see this equation, we can think, well, so it is trivial, because if it is linear, nothing very complex can emerge from it. But, well, this is not the case. Because of the Lagrange multiplier, say this Lagrange multiplier that enforces the spherical constraint and forces the system to flow on the surface of this n-dimensional sphere, will introduce non-trivial behavior, and in particular the phenomena of aging and memory. We will see that it emerges in this system. So, well, we have to solve this equation, but as it is a system of linear equations, coupled, like in harmonic oscillators, well, the way to solve it is to decouple the equations through an orthogonal transformation. because the Jij matrix is symmetric, there is an orthogonal transformation from which we can change the basis from the original basis of the spins to the basis of the eigenvectors of the matrix. In that basis, the system will be decoupled, and we will be working with the distribution of eigenvalues when we diagonalize the matrix. So that's why, in the end, when we take the n going to infinity limit, we will make use of the Wigner law in order to solve the dynamics. Up to here, the equations are exact in the sense that they are valid for any n, for arbitrary n. So in particular, we can do simulations, for example, for arbitrary n, and study the system. Okay, so this is linear algebra. Nothing new. This is the same system of equations written in matrix form. We can apply an orthogonal transformation and diagonalize the matrix J. So this is the eigenvalue equation. Lambda k are the eigenvalues of the matrix J. They are characteristic of this Gaussian orthogonal ensemble. I don't know if you know, the ensemble that defines the disordered matrix. It can be different, so we choose an ensemble in which the elements are real Gaussian random variables. So there is a particular ensemble that describes this kind of random matrix, and the distribution in the n going to infinity limit is the Wigner law. But if we choose a different kind of random variable chosen from a different distribution, this distribution of eigenvalues will be different. But this is as usually with Gaussian things, it is quite robust. So the first attempt is to use Gaussian entries for the couplings. Why will be the variables in the rotated state that will correspond to the basis of the eigenvectors of the matrix J? So this is the way we change basis, say from S to Y, using the orthogonal transformation. So in the new variables, in the Y variables, the Langevin equations have been decoupled. So now we have a single equation for each degree of freedom, decoupled from the other. The only thing that will couple them comes from the Lagrange multiplier. This lambda I are the eigenvalues. There is new external fields and noise, say in the new basis that are defined in this way. And it turns out that, for example, the noise that we will use it to compute averages has the same properties of the original noise. So the noise in the new basis also, of course, has an average value of 0 and delta correlations with proportional to the temperature. So exactly the same statistics. Well, this equation is easy to solve. The solution for Y, that are the degrees of freedom in the rotated basis, in the basis of the eigenvectors of the matrix J, is given by the solution of the homogeneous equation. Say up to here, we have the homogeneous equation, essentially an exponential. We separate variables, and the solution is given by an exponential. So the term that comes from the eigenvalue is given simply by this exponential of lambda IT. And the exponential that comes from the Lagrange multiplier, well, we have to integrate. So as we still don't know what is Z of S, we have this implicit term here. We will, in the next slide, see how to compute S. And then there is a particular solution of the non-homogeneous equation when we incorporate here the term of the external field and of the noise, and a kernel that is similar to the solution of the homogeneous equation. So it is the standard solution of this ordinary differential equation. So this is the exact solution. You see that it depends on the realization of the noise. Here, it depends on the realization of the noise. It depends on the spectrum of eigenvalues of the J matrix, and on the initial conditions. These three ingredients, each of them are important for a disordered system, because if we think of that rough energy landscape, we can imagine that, for example, the initial condition is very important. If we let the system relax after a sudden quench from an initial condition near a local basin of attraction, near the local minima of the landscape, it will relax initially to that basin, and will stay that maybe for very long times. So the initial condition matters differently from systems with fast and simple relaxation and unique low temperature state or a unique ground state. So initial conditions are here. Are here. Well, the distribution of eigenvalues, of course, this is the statistics of the disordered matrix. Well, and the noise, We are looking at a non-equilibrium dynamics. This is a classic non-equilibrium dynamics, the Langevin equation. It's a, say, prototypical dynamics. Again, we can work from here numerically, for example, and we have the exact solution of the model. Now, well, up to this point, excuse me. Up to this point, temperature is arbitrary. So this is the solution for arbitrary temperature because we have the noise term here. But we will particularize from now on to zero temperature, that we will make things simpler. So at zero temperature, the average value of the state variables, y, is given by the average value of the first term in the previous slide. So at zero temperature, this term goes out, especially for one-time quantities, because the average value will be basically proportional to the average of eta I, that is 0. So this integral disappears, and we have to compute the average value of the first term. So this is the first equation there, where gamma is the exponential of this integral of the Lagrange multiplier that we will be determining in a minute self-consistently. So in order to fix the Lagrange multiplier, we define the autocorrelation function, the 2 times autocorrelation function, defined in this way. Well, it is easy to see that we can change basis and write the autocorrelation function in terms of the rotated state variables. And then this sum will be given by gamma of t prime, because we'll have, say, this multiplied at time t times the same multiplied at time t prime. So we have this product of the gamma function at t and at t prime, plus the sum, 1 over n, the sum of the square of the initial condition and the exponential of lambda I t minus t prime. Okay, now if we impose the spherical constraint, say we make t equal to t prime, this will be the sum of Si of t squared. That is exactly the spherical constraint. This sum over n have to be fixed to 1 at any time. We said that the Lagrange multiplier is a function of the time. At any time, the spherical constraint has to be satisfied. So if we make t prime equal to t, this will be 1. This left part of the equation will be 1. And we end with this relation, 1 over gamma squared equals to this sum. So z is equal to minus the derivative of the logarithm of gamma of t with respect to t. So it will be the logarithmic derivative of this quantity, basically. So you see that for any n, no, up to now, all is exact for any n, for any size of the system. So this is the equation that defines the Lagrange multiplier. It depends on the initial conditions and on the spectrum of eigenvalues. Again, we can work numerically from now on and compute the Lagrange multiplier. But now we will come back to the computation of the 2 times autocorrelation. That is the quantity that we saw. It describes the phenomenon of aging and of memory. So let's come back with this value of Z. Take the thermodynamic limit, or better saying the limit when n goes to infinity, that it's not exactly the thermodynamic limit. Let's work with a particular kind of initial conditions. Say we can choose any initial conditions up to this point. We can initialize the system near an equilibrium point, near a local equilibrium point, or, for example, in a high temperature initial conditions. Because we are now interested in quenches from a high temperature state to a low temperature state, we will initialize the system in a high temperature initial condition. So initially, the spins are completely disordered. So in the spins in the original basis, we can think that they have the same projection onto the basis of the eigenvectors. So for the y variables, a disordered initial configuration that is characteristic of a high temperature initial condition, in this configuration, the y variable will be equal to 1 for any n. So the same projection of the spin into each of the eigenvectors of the matrix J. Say pure states, if you want, pure state will correspond to a particular eigenvector of the matrix, and in that case, the projections would have only one y different from 0 and all the others equal to 0. So localized state, this kind of extended state, high temperature initial state. So this initial condition formally is very simple because all the variables are equal to 1. In the thermodynamic limit, 1 over n versus the sum over m turns to an integral over the density of eigenvalues. So when n goes to infinity, this sum goes to the integral over the density of eigenvalues, say rho of lambda. And here we will use the Wigner semicircle law for the density of eigenvalues. Okay, we can go on, come back to the expression that we already obtained for the 2 times autocorrelations. Here in the limit, in the n going to infinity limit, we will have this integral of the exponential of lambda t plus t prime plus the the density of eigenvalues. Remember, this was the expression of the 2 times auto-equilibrium function for a particular realization of the disordered matrix. So now the initial condition equals to 1. So the only term here is the exponential. In the thermodynamic limit, this has to be multiplied by the distribution of eigenvalues. And this integral has an exact solution, an exact result in terms of these modified Bessel functions. So this is the exact result at t equals 0, at 0 temperature, for the 2 times autocorrelation function. Again, we can impose the spherical constraint, making t equal to t prime. And if we do that here, we obtain this expression. And from this, we get gamma of t, that is a function of the Lagrange multiplier. So we have determined self-consistently the Lagrange multiplier. So, well, this is the exact solution for the 2 times correlation and for the Lagrange multiplier. In the next 10 minutes, we will analyze the 2 interesting time regimes, that is the quasi-equilibrium regime. Let's see how this collapse of the curves when the difference of the time is small emerges from this exact solution.
Sorry?
And also the aging regime.
This L, what is it?
This?
It's the Bessel function. Yeah.
Excuse me?
This L is the Bessel function, and then, okay, no, I understood.
This? Excuse me, I don't.
I didn't understand
let me
what
know.
was the I1.
Let me know what we are talking about.
So this integral solves like a Bessel function, and I didn't understood this notation of
this I1.
L, but it's I1.
Okay. Yeah, this is the result of this integral. This integral has an exact solution, and the exact solution is given by this modified Bessel function of 2 times t plus t prime over t plus t prime. This is the result of the integral. Okay? So we have the exact solution. These functions, well, we will see in a minute. Asymptotically, see for large arguments that we will be interested in, it is basically an exponential. Okay? So, so we can plug in the results onto the expression of the autocorrelation. This is the result. It is useful to define this scaled variable, u, that is t prime over t. We will see that in the aging regime, the autocorrelation will depend solely on u. So this is a scaling regime. But first of all, we can compute the quasi-equilibrium regime. That is the development of this plateau, in which the dynamics is time translation invariant. So now, when we want to extract these results, we have to be careful with the time scales, because, say, the critical point of these slow dynamics in these disordered systems are time scales. In this model, there are only 2 important time scales that are associated to this quasi-equilibrium regime and to the out-of-equilibrium aging regime. But in more complex models of spin glasses or the disordered systems, there are a hierarchy of time scales. And this is really complex, say, in order to disentangle all these different time scales. So here is rather simple. So that's why I think that this model is pedagogical, is didactical. So in order to extract this quasi-equilibrium regime, we consider large times, t and t prime are large, but so that the difference, t minus t prime, the tau that we defined earlier, is small compared to each of the two times. In particular, t minus t prime over t goes to 0. It means that the difference between the observation time and the waiting time is very small compared to t waiting or compared to t. So we wait for a long time, then we begin to measure, and we measure up to times that are much smaller than this waiting time. Okay? So in this regime, we are in the quasi-equilibrium regime because during a long waiting time, the system entered this sector of phase space in which it gets trapped for long times. And if we begin to measure exactly after this time and for small times, we will see a system that, for all practical means, it is in equilibrium. So the dynamics in particular is stationary. It is time translation invariant. So this is the quasi-stationary regime. T prime large, but epsilon, t minus t prime over t or over t prime goes to 0. And u goes to 1. Say both times are large and goes to 1. Well, here, this is an exercise that I put as exercise to you for the last lecture on Wednesday. We can, but it's very simple to compute it. We can do the calculation in this limit. As the times are large, we can approximate this modified Bessel function that is given by a series. The dominant behavior is given by the exponential of the argument divided the power law, x to 1/2. So when one substitutes the Bessel functions with this approximation, you will see that if you work out the calculation, that the exponentials drop out, and we end with this result that has this epsilon fraction, and the leading behavior goes to 1. Say when epsilon goes to 0, this goes to 1. This should be the value of the autocorrelation function in this regime that, as I said, it is this regime in which tau is small, much smaller than t waiting or than t. One is particular of the t equals 0 case. Here, this numerical result is for a temperature slightly above 0. So the system will relax to a different, not to 1, but to high, but different from 1 value. But at t equals 0, the system is completely frozen in this regime. So the plateau, the plateau is at c equal 1. Okay, now we would like to see the departure from this quasi-equilibrium regime. That is, it will be the aging regime. This is another in which tau is large, at variance with this in which tau is small as compared to t or t prime. Well, these results were first published by Letizia Cugliandolo and David Dean, say in the 90s. They are very well known. And from then, it turned out that this phenomenology appears in many other models and systems. Okay, so to finish today, let's see the aging regime. The aging regime is defined in this way. This is the time scales. Again, t and t prime are large, go to infinity, but u, that is the relation between t waiting and t, is between 0 and 1. So at each particular value of u, we will be defining a scale in times between t and t prime. Well, we can again work out the asymptotic values of these relations between Bessel functions, but now in this regime, making u finite. In the quasi-equilibrium regime, remember that u went to 1. Here it is smaller than 1. So we have to extract tau from these relations. And if we do that again, it is an exercise. You will see that this quantity depends only on u. Well, we can plug it again here. The other part, it is easy to see also that it will only depend on u. So the autocorrelation function is a function of a scaling variable, that is this t weighting over t. In particular, it goes algebraically with u. Say if u is very small, it goes as u to the 3/4. And this, if we plot this, we will obtain these different curves, the different relaxation curves for different waiting times. This is increasing waiting times. You see that they are parallel to each other. That is a signal that there is a scaling. So if we should plot c against u instead of tau, all these curves would collapse onto each other because c is a function of u only. So this is the aging regime. The fact that there is a scaling in the 2 times correlation function as a function only of this u. In more complex models, in fact, the scaling is a function of more complex dependencies on u, not simply on u, but on functions of u. But this SSK model is the most simple one, and these 2 times quantities depend only on u. If you work out the response function that we defined earlier, say the complexity of the computation is the same. It is a simple computation, and you will see also that it shows the quasi-equilibrium regime and the Asian regime also in the response. So this is a general phenomenology for any observable, for any 2 times observable for this kind of systems. Okay. Let's go out. So these are the exercises of the day. I think we can try to work out them in detail on Wednesday after the third lecture. Well, they present no difficulty. Okay, and I think that for today, yeah, I will stop here.
Thank you.
Could you repeat, maybe if you go to slide 8 or 9, why did we introduce the fields which couple to the spins? I kind of missed that, I think.
I don't know if I understood your question. The fields that couple to the spins?
If you go to slide 8 or 9, I think that's where I missed that. Eight or 9, slide 8 or 9.
8 or 9. 8.
Here we introduced this term HISI, but I mean maybe I'm not familiar with this formalism. But why did we do that?
This is an external say, magnetic field. This is an external field coupled linearly to the basic degree of freedom of the system, that is the spin. So this is the coupling between the external field, magnetic if you want, any external field, and the spin. It is useful if you want to compute response functions, because you know responses are computed by applying a small external field and then putting it to 0. We haven't computed the response function, so I haven't used it. But this is an external field. It couples in this way, linearly to the spins. If you should compute the response functions, you will have to go through the variation of the Hamiltonian with respect to the external field. So you will need this term. Here it is, say, it is inessential because I didn't work with it.
But then maybe a technical question. If you would have the fields, I mean, I'm coming from a quantum statistical perspective, would you then use the GUE because time reversal symmetry is broken? Or we can still work in the GOE for the couplings, I mean.
What is GOV?
GU, the unitary, Gaussian unitary ensemble.
For the disordered variables?
Yeah.
Well, no, the ensemble, it is the ensemble that describes the disordered variables. So if the variables are complex Gaussian variables, yeah, you have to use another Gaussian ensemble corresponding to complex variables. This is the Gaussian orthogonal ensemble in which the Jij are real Gaussian variables. But if they are complex Gaussian variables, yeah, it is the GUE ensemble, if I remember well. It is another ensemble. It depends on the nature of the variables.
Yeah.
Okay?
Okay.
Yeah, it depends. Here is because I am choosing the J matrix with entries that are real Gaussian variables. So the ensemble that describes them is the Gaussian orthogonal ensemble. If you choose another kind of variable, for example, complex, the ensemble is another.
Yes.
It's different, of course. You have to work with the ensemble that represents the particular kind of random variables that are describing the disorder in this case. Okay?
Any other question?
Yes. What happens to all these results for the spherical model for a large but finite n?
For finite n, well, basically, the phenomenology is the same, but it appears a different scaling regime, another, not a different. So you will have this aging scaling regime that is asymptotic, and when you introduce corrections with finite n, there is another intermediate regime in T that is also algebraic. It is also a power law, but it decays faster than this asymptotic regime. So it is more complex when you work with a finite system. Yeah.
Thanks.
I was wondering, in this case, with the noise, are you still doing quench?
Yes.
Okay.
Yeah. We
A
are
quench
studying quench
in the temperature.
In temperature, yeah.
Would it be the same thing if I do the quench in the magnetic field?
I think that, yeah. I haven't think about that especially, but yeah, you can do a quench in the parameters of the system, in the couplings or in the external field. You can change, say a quench. You can change the value and look for the response, what the system does after a quench in any of the parameters. Yeah, you can do it.
Okay, thank you.
I don't know what are the consequences of doing a quench in the field, for example. But in principle, yes, you can do it. Yeah.
So, thank you again.
Okay. Thank you. Okay. See you tomorrow.
There is a list rolling around for the presence. How do you say presencia in English? Exactly. For the attendance. So please sign that up and give it to me. That's it.